So let's do another example, one that is going to be a little more quantitative with some values. And we're going to be changing the magnetic flux again, but this time the area will remain constant and the magnitude of the magnetic field will be changing, okay? So we're dealing with that other case of changing flux, where flux is changing because the magnetic field is changing with time. So let's read this example carefully. So we have a uniform magnetic field pointing out of this loop with a magnitude of 1.5 Tesla. And it's pointing out of the loop at an angle. And look at how this angle is described. It's described as being 60 degrees to the plane of the loop. Okay, so that is going to be this angle right here. Okay. And then we're given the diameter of the loop. And the question is, what's the magnetic flux? All right, so what's the magnetic flux? That's simply asking you for what is BA cosine theta, right? Second aspect of part B, what is the induced EMF if the magnetic field starts to decrease from 1.5 Tesla to 0? Okay, so that's going to be asking you what is EMF. So let's answer part A. The first part of part A is what is the flux? Well, flux is BA cosine theta, right? We know we're going to be using that cosine component since we have an angle given to us. But we need to make sure that we're using the correct definition for theta. Theta, just as we did in chapter 17 with electric flux, theta is going to be always the angle between the area vector of the area and the B field, okay? So the 60 degrees is not going to be what you put in this formula, okay? You're going to have to do a little bit of geometry, and what you find is that the angle you need to put in there is 30 degrees. Okay, and why is that? Because this angle was defined with respect to the plane of the loop, and what we need is the angle between B and A. So where A is the vector perpendicular to the plane of the loop. Okay, that's the area vector. So that's pretty much the x-axis here. So we're going to just, plug and chug this guy. As long as you carefully, use your, the correct angles. Now for the area, we're going to need to calculate the area. We're told that the diameter is 3.5 centimeters. So we're going to need to use the radius, which would be 1.75 centimeters. Or 0.0175 meters squared times pi r squared, right, for the area. And then cosine of 30. So plug that in your calculator. Okay. So we get 0.00125. So that is, what are the units of flux? Those are called Webers. Okay, the units of flux is a Weber, which is a Tesla meters squared. Okay, that's a Weber. Named after a physicist. So there's our flux. Now the second aspect of part A, what is the induced EMF? So let's write down what EMF is. And we can do the magnitude here. Okay, it's going to be delta phi over delta t. Let's expand what phi is. Phi is B A cosine theta. Okay, let's take out all of the variables that are not changing with time, right? Is the area changing with time? No. Is the angle changing with time? No. So what is changing with time is the magnetic field. And so let's rewrite that. A cosine theta. And so delta B, final field minus initial field, right? Delta is always final minus initial. And our final, so let's read this carefully. What is the induced EMF if the loop, if the magnetic field decreases to 0, right? So the final field is 0. Let's do this. Let's write delta B over delta T as 0 minus 1.5 over, now let's see, what's the time? Part B. So technically we're working on part B. They kind of slipped it in on us, right? So 10 seconds, right, for part B. That's the time that was taken to go from 1.5 Tesla to 0. Okay. So that's going to give us a negative 1.5 Tesla over 10. Let's plug that back into our EMF equation right here. Okay. Let's go ahead and plug everything in. Area was pi r squared cosine theta, cosine of 30, and then delta B over delta T is negative 1.5 Tesla over 10. So now we put everything in the calculator, and we're going to ignore the negative sign, right, because everything we're doing is a magnitude. And what we're going to get is the same thing we got before, but a couple of decimal places over, right? So 0.000125. Units of that is a Weber per second, but that is also a volt, right? Because an EMF is a voltage. So let's skip Weber per second. That's kind of a silly unit. It's a volt. And so there's another way we could have solved this problem. Okay, I kind of did it in a way just to illustrate the idea that any one of those three components of flux can change with time. Another way to do this problem is the EMF is the change in flux with respect to time. Well, what that is saying, it's the flux final minus the flux initial over the time, right? And in part A, we calculated the initial flux. The final flux is 0 because B is 0, right? So we would do 0 minus our answer for part A, which is the initial flux, right, at 1.5 Tesla. Over 10 seconds, and we get the exact same answer. We're going to get rid of the negative sign since we're dealing with just the absolute value for right now. Of course, I wrote the negative sign anyway. Just can't help myself. Right, we get the exact same answer. 0.00125 divided by 10, that just moves the 0 over, right? Volts. So, right, if you know the flux already, go ahead and just do it, right? This way obviously makes a lot more sense than this method I did earlier. But I just wanted to show you, in case you're not given the flux in the beginning, right? You get to see it, and you get to see it happen both ways. So part C is just changing that delta T to 0.1. So let's do it the easy way instead of recalculating everything, right? Typing all that stuff in the calculator. So now our initial flux, we already know our final flux is 0. Was it 0.1 seconds? Now we're dividing by 0.1. So we're going to get absolute value negative 0.00125 Webers divided by 0.1. And that's going to move our decimal the other way, right? It's going to move it to the left. It's going to increase the magnitude of the EMF. Volts, right? Now we have more volts than ever before because we changed that field much faster. Okay, so the faster the rate of change, the higher the EMF. Okay, right? We can see that here because if delta phi over delta t is fast, right, is big, then the EMF will be big. So the faster you change your field, the bigger the voltage you will get. Okay, it's an important concept. Okay, now this is an interesting got the concept. Let me go ahead and erase this stuff real quick, okay? So what if instead of a copper loop, like in that previous example, what if we replaced it with wood? Okay, you already saw the answer. Well, so let's explain why. What if we replace it with wood? The question is, what would happen if, to the EMF, if it was wood, right? If we, instead of having a piece of copper here, we had a piece of wood. And now, you and I know wood is not a conductive material, right? It's not like copper. It's not like a metal. It's very difficult to conduct electricity. So if I were to, put a magnetic field through here, change it with time really rapidly, how much EMF would I get? Well, guess what? The EMF would be exactly the same. Okay, why? Let's look at the equation. Delta B, or delta phi over delta T, right? And delta phi over delta T is BA cosine theta delta T, right? There's nothing in here that, explains what the conductivity or resistance of that material is, right? The only thing in there is the magnetic field, which is created by some outside source, the area of the loop, which is a geometrical factor, and then the angle between B and A. So that's just really proving to you that this changing magnetic field, it's creating an electric field and thus a voltage, no matter what the subject is, right? No matter what. If it's, a loop of wood, a loop of bone, a loop of copper, okay? It doesn't matter. But you may be asking, well, that's weird because, wood is not conductive. Well, that's okay. Because that doesn't mean that the current that flows through the wood is going to be high, right? Because V equals IR and I equals V over R. So the larger the resistance, wood has a very large resistance, the smaller the current. So the current flowing through that wood is not going to be very high. Of course not, because, resistance is gigantic for wood, but the EMF will be the same, whether that EMF is created by, a changing magnetic field or a changing area or a changing, theta, right? That EMF is created by a changing flux. And it doesn't matter what that loop is made out of, okay? So it's a pretty interesting idea here. And so just to wrap up this section, we talked about two different types of EMF, right? Motional EMF, because a conductor is moving in a magnetic field. Motional EMF usually is changing area, right? Because in order to get something to move, right, it's changing the area. Where there's other examples of motional EMF, which we will look at very soon. And then an induced EMF appears in any loop subject to a changing magnetic field, okay? And motional EMF and induced EMF, you use Faraday's law to figure out how much EMF is produced, right? And Faraday's law is simply that the EMF or the voltage produced is the change in flux through that area over the change in time, okay? And there's three ways to change the flux. Change it by changing the area, by the magnetic field, or the angle, okay? So let's move on to Lenz's law, right? So we looked at Faraday's law, which told us the magnitude of the EMF, but it didn't tell us anything about what direction the EMF is and what direction the resulting current would be. So Lenz's law is going to give us the direction aspect of Faraday's law. And we're going to use a right-hand rule, okay? But it's a special one. It's got a couple of steps to it, okay? But it's going to be another right-hand rule. So let's take a look at these figures again, all right? Where we were moving a loop towards and away from a magnet. So let's look at this guy on here on this side, right? As we're moving this loop towards the magnet, what's happening is the magnetic field is getting stronger, right? The magnetic field that is going through the loop is getting stronger because we're bringing it closer and closer to the magnet. So the magnetic field is getting stronger. And we saw that a current was induced in this direction. Well, that current that's induced, you know what it does from chapter 20. It creates a magnetic field, right? Currents create magnetic fields. And that magnetic field, its job, okay, that magnetic field being B loop, its job is to oppose the change in flux that originally created it, right? So notice in part B that B loop is pointing opposite to the magnetic field direction. It's pointing opposite to decrease the increasing flux because that's what B loop does. It opposes the change in flux. And where does B loop come from? B loop is created by the induced current that we saw in the previous sections. Okay, and so the idea here is to figure out the current direction. You're going to kind of work the other way, right? We know that the change in flux produces a current, and then that current produces a magnetic field. But in problem solving, to figure out what direction the current is, you're going to first figure out what direction B loop is, and then do the right-hand rule to see the current direction. And so the rule for B loop is that it always opposes the change in flux. Opposes change in flux. So the flux is increasing, right? And the magnetic field is pointing to the right because that's the direction it goes towards the South Pole. But B loop is going to oppose that increasing magnetic field by creating a magnetic field in the opposite direction to oppose the change. And then if you stick your thumb in B loop and you're going to curl the fingers around the way they naturally go for your right hand, you're going to see that your fingers are going to curl kind of into the page here. So you can't see my fingertips, right? They're curling into the page based on the right-hand rule for current in magnetic field. So let's now look, right? So this is a case of increasing flux. Let's look at the case of decreasing flux and see that opposition, okay? So the magnetic field that is going through the loop is getting weaker now because the loop is moving farther away from the magnet. And B loop is going to point in a direction that opposes that decrease. Well, how do you oppose a decrease? You're going to add more in the same direction, right? That's how you oppose a vector pointing to the right that is getting smaller in magnitude. You're going to add more vector in the same direction, right? To oppose the decrease. Add more back in. And that's the direction that B loop is going to point here because the flux is decreasing. So B loop's job is to oppose that decrease by creating a magnetic field that will point in the same direction. And so then you do the right-hand rule. Your thumb is going to point in the direction of B loop, and you're going to see that the fingers of your right hand are going to curl towards you. Okay? And that's going to be the direction of your current, right? And you can see that clearly now. So you're going to have a counterclockwise current, right? If you're looking this way. If you're looking this way, the current is counterclockwise, right? It's going from 9 o'clock to 6 o'clock to 3 o'clock, right? So that is basically, summarizing Lenz's law. A new magnetic field is created by the induced current, and it will always point in the direction that is opposite to the change in flux. So Lenz's law summarizes this. The direction of the magnetic field induced within a conducting loop opposes the change in the magnetic flux that creates it. So you notice that Lenz's law, it only talks about B loop, right? And the flux change. It doesn't talk about I. It doesn't talk about the induced current direction. So what you do is you first figure out what direction B loop will point. What direction the induced magnetic field that opposes the change will point. And then you do the right-hand rule on that magnetic field to find the current direction, okay? And so now that we know the direction, Lenz's law and Faraday's law are combined, and the magnitude bars go away, and what we have is a negative sign in front of our change in flux. The minus sign indicates that the current caused by the EMF induces a magnetic field that opposes the change in flux. Okay, the magnetic field that is created by the induced current opposes the change in flux. So to figure out the current direction, you should just figure out what direction the magnetic field resulting from it would need to point to oppose the change in flux. Let's use this Lenz's law in the situation of the sliding copper bar, the very first example that we looked at. And remember, we were sliding it to the right, and that increased the area, right? B was remaining constant, but the area was increasing. And so that caused a flux change, right? Because you can change the flux in three different ways, right? In this case, we were changing the area, and that area change was increasing, right? Because we're making the area bigger. And so what direction is B loop going to point to oppose an increasing flux? It's going to point in a direction opposite to the field, right? To reduce the flux, because its job is to oppose the change. Nature does not like change, right? Many people don't like change. Some people really thrive on it, but nature doesn't like it. And all of these kind of weird phenomenon that kind of come out of nowhere, they're coming out of nowhere to oppose changes. So this is a very perfect example of that situation. So B loop is going to oppose the change in flux by pointing down, all right, opposite to the field that is in the problem. And so then you're going to stick your thumb down of your right hand. Let's see if I can draw this. Your thumb is going to be pointing down, and then your fingers will be curling kind of into the page there, right? You can't really see them because they're pointing into the page, and you can see that your fingers are going to curl around in a clockwise direction as viewed from above. Okay, right? If I'm looking at this from above, that is going to be a clockwise direction, right? 12, 3, 6, 9, right? Going clockwise. So the moral of the story here is that B loop points opposite to the increase in flux, okay? And so to find the induced current direction, we do the right-hand rule on B loop. And then our fingers will tell us the current direction, okay? And so now we can confirm, right? This was the current direction that we saw from the first example. Oh, so that's what I have here in this section. I'm going to go to the next lecture here. Okay. I had kind of an overlap. So you can go through these notes again. All right, so this is where we left off. Let's take a look again at Lenz's law, right? And what is it telling us? Well, Lenz's law refers to a change in magnetic flux. So anytime you're looking at a magnetic flux change, you need to figure out, is it increasing or decreasing? Okay, right? We're noting the change of the flux, not necessarily the direction of the field that causes the flux, but Is it getting bigger or smaller? And then the B field, B loop, will point in the direction that reduces or opposes the flux. Okay? So that's kind of what, here we go. Let's look at this, got the concept. And remember, we're going to ask ourselves first, is the flux changing, or how is it changing, increasing or decreasing? So we have a rectangular loop of wire. All right, it's right here. And it's moving to the right. So this is going to be another motional EMF, right? Because we're inducing a flux change through motion. So it's a motional EMF. It's moving to the right. And it's entering more and more into a magnetic field, okay? That's pointing into the page. So as this little loop, skinny loop, moves to the right, more and more of it is going to be in the field, okay? So let me ask you, is that an increasing or decreasing flux? That is going to be an increasing flux. Why? Because the area that is exposed to the field is increasing, right? So B dot A is going to be getting bigger, right? The flux is going to be increasing. More of the area is exposed to the field. And so now that we understand that B is increasing, we know that the direction of the induced magnetic field will oppose the increase. And so in order to oppose the increasing flux, it's going to need to point in a direction that is opposite to this magnetic field. So that would be out of the page, right? So this is B loop. That B loop is caused by the current moving around in this loop due to that changing flux. So now that we know B loop, we can figure out what direction the current flow is. So you're going to stick your thumb out of the page in the direction of B loop. And then you're going to see, if you're looking down at your hand, that your fingers are curling in the counterclockwise direction. Right? They're curling around like this. Counterclockwise. If you're looking down at your hand with your thumb sticking up at you. Okay? Your fingers will naturally curl in the counterclockwise direction. And so there we go. That is the answer. That is the direction of the current around that loop as it's moving into the field. Because the flux is increasing. And so B loop will oppose the increase by pointing in the direction opposite to the existing field. So, right, and so the steps here, we first need to figure out how is the flux changing, okay? It's increasing. Increasing flux means that B loop will point in a direction to decrease the flux. B loop will point out of the page opposite to the field in the problem. And then we're going to use our right-hand rule for B loop. I should write that for B loop. Okay. And you point your thumb in B loop direction. And then you're going to see your fingers curling in the counterclockwise direction, okay? So, look, I want you to kind of look at this problem again if the loop is leaving the field, okay? So do that exercise. What if loop was leaving the field? Okay, ask yourself that. And go through these steps. So now let's look at part B, or the second aspect of this, got the concept, right? So now, what if the loop, let's read it carefully. What if the loop is moving, but it's completely inside of the field region, okay? What would be the direction of the current in the loop? So it's moving around in that field region. So it's just, it's going to be scooting over here. It could be scooting over here. Okay, it's scooting over here. It's moving around in there. What's happening to the flux? Is B changing? No. Okay, is B changing? No, it's not. Is the area in the field changing? No, it's not. So there is no flux change, right? No flux change at all. And therefore, if there is no flux change, then there is no EMF. And then if there is no EMF, then there is no induced current, okay? Current is 0. So, right? Makes sense. Go back and do this idea, okay? And see what happens. Does the current direction change if the loop is moving outside? Okay, I want you to do that exercise yourself. So to wrap up this section of Lenz's law, right? All we did wasn't really like, it was a lot actually. It's a lot of concept. And there's a couple of steps to it. We were able to figure out the direction of the induced current that is created by the EMF due to the flux change. We use Lenz's law. Lenz's law states that the magnetic field that's induced by the induced current, right? It's created by the induced current. That magnetic field is going to always point in a direction that opposes the change in flux. So we must examine what direction. Is it increasing or decreasing? What's going on with the flux? And then B loop is going to oppose it. Then we're going to do a right-hand rule on B loop and find the current direction. So that's Lenz's law. Okay, it's very conceptual. On the exam, there'll be tons of pictures. Okay, what direction is the induced current? What direction is this? What direction is that? Okay, so be prepared for that. Final section. All right, what did we talk about so far? We talked about flux change due to area change, right? We talked about flux change due to magnetic field magnitude changing. So the final step in creating an induced EMF is by examining flux change due to the angle between B and A changing with time. And guess what? This is how alternating current is created. Okay, so we're finally getting to that little teaser I did in the beginning of this lecture, right? How do we create alternating current, which we use everywhere for everything? Okay, this is how we do it. We keep B constant, we keep the area constant, and we spin things around, right? We're spinning that loop around in the field, generating an EMF. And the faster we spin it, the more EMF we get. So let's take a look at that. This is called an AC generator. So that idea of just spinning a loop of wire in a constant magnetic field, we call this an AC generator, okay? So if we look at a coil of wire that has, n number of turns and some constant area A, and we spin it around in a magnetic field, what we see is that the angle between B and A changes, right, with time. How do we describe a changing angle with time? You might remember from Physics 1 and maybe Chapter 5 or so, where you started to look at rotating things. You might recall this, right? Omega is change in angle with respect to time, right? That's a speed, right? It's an angular rotation speed. So we can solve for theta and express theta in terms of its speed, right? Because we care about theta, because theta is the angle and theta goes in our flux equation. So we're going to kind of take that speed, convert it back to theta in the same way that we would do for velocity, right? Velocity is distance over time. So to solve for distance, we would just put the time right here, right? We're doing the exact same thing here. So we're going to characterize this change in angle as omega, and we're going to express that, whatever angle we're at some time is simply omega t, plus some whatever the initial starting point is, okay? Which is usually 0. So we're usually going to assume that phi is 0, that we're starting at 0. But if we didn't, the problem would say if the angle starts off at 30 degrees, and it has a speed of 2 radians per second or something like that, right? Then you would plug in that 30 degrees as your phi. It's just your starting point. And so then the EMF is going to be the change in cosine of theta t plus phi with respect to time. And there's some math that goes along here that we're kind of skipping for a reason. That delta cosine delta t becomes a sine. Okay, and you're just gonna have to just trust me on it. It's some calculus. Okay, so calculus comes into play here, but we are, not subjecting you to it. You're just gonna know that this change in cosine with respect to t becomes the sine. Okay, this is what it does. This is what happens. And then of course that theta, I put theta here, my bad. That whole thing here, this is actually theta, right? This is how we express theta. It's omega t plus phi. So that's all theta. And then omega comes out front because of that calculus. And then we have our number of turns, area, and magnetic field, right? Like we normally do in flux. So this is the equation for the EMF that's generated by an AC generator, which is simply just a coil flipping around in a constant field, okay? Constant A, constant B. The only thing that's changing with time here is the angle theta, okay? And so, the EMF that's produced, it's a sine function, right? It looks like a sine function with a bunch of factors in front of it. And so, what does a sine function look like? It looks like this, right? It starts 0 at 0. The max value here is going to be W nab. I like to call it W nab. Omega and AB, right? W nab. And its minimum value will be W nab, right? With a negative sign. And so that's how much EMF you're going to get from a generator, okay? The max you're going to get is W nab. And since current is proportional to EMF, the max current you're going to get, how do we figure that out? Well, remember that V equals IR, right? Or EMF equals IR. Since EMF is just a voltage, I is EMF over R. So the current max will be EMF over R, which will be W nab over R. Okay, so that's how much current you're going to get out of an AC generator, okay? Depends on the number of turns, the area, and the magnetic field, and of course the resistance of the coil, and the speed at which you're rotating. So the faster you turn it, the more current and the more EMF you get, right? The faster the rate of change, the more EMF and the more current you're going to get. And you know that already because remember when we looked at delta B over delta T changing at 0.1 seconds from example 2, 20.2, we saw that the EMF got bigger, right? So it makes perfect sense why omega would be here proportional to I and V, because the faster that we change the flux, the more EMF we get. So, the EMF produced by an AC generator, it's going to change from positive to negative, right? Because it's as a function of sine. Oh, here's the current. This is what I wrote before, right? This is the current. It's just the EMF divided by R. But what doesn't change with respect to time is the power that this generator creates, right? And power is an important quantity. That's the rate of energy change with respect to time. So it's like we want to know how much energy we're delivering to the things that we're powering, right? So that's why we look at the power. So if we want to convert current to power, you might remember this from chapter 18 briefly, right? Power is I squared R. So we're going to square that term for current, multiply it by the resistance of the object that is hooked up to the generator. And when we square all that, we get this formula right here, okay? So you can just, this is a formula you can use verbatim. So this is kind of like this last section of chapter 20 is very plug and chug. So, you know, just keep these formulas in mind, know how to properly use them, and you will be good to go. Okay, so this is the power. And you can see why everything's squared, because this power is obtained by squaring the current and multiplying it by the resistance of the object that the current is powering. So just as, you know, kind of like a summary, right? The voltage produced by an AC generator, it's of course going to vary from positive to negative because it's a function of sign. But the power, since it's squared, you're only going to get positive values. And that makes sense because power is proportional to energy, and, you know, we don't have negative energy. We haven't discovered that yet. Energy is always positive. You can have changes in energy as negative, right? You can have a delta U as negative, but U in general is not negative. So let's do, okay, yeah. So what I did is I'm pulling some homework problems. You weren't assigned these problems, but I'm pulling some problems from the back of the book, from the homework section, because I didn't quite like the examples that were in the slides. So let's do a couple of these problems together, okay? Let's read through it. And so we have a rectangular coil, and we're given the sides of the coil, okay, so that we can find the area. And the number of turns, 500. And then this coil is rotated about its long axis. So that's what this means, right? If it's a rectangle, then if it's rotated about its long axis, then the axis of rotation is along the long side, okay? And so you're going to see that this rectangle rotating either, you know, this way or this way, right? About the long axis. And there's a magnetic field of 0.58 Tesla directed perpendicular to the rotation axis, okay, right? If this is the rotation axis, then this is perpendicular to that. And the question is, what frequency must the coil be rotated for it to generate a maximum potential of 110 volts, right? So we want the EMF to be 110 volts. And we want the maximum EMF to be 110 volts. So the maximum EMF is given by W nav, right? Omega NAB. Omega is going to be the frequency that we rotate, right? It's a frequency because it's in radians per second, right? Anything per second, you know, is a frequency. So radians per second is, I don't know why I put that there. Radians per second is a frequency. So we're solving for this, for omega. And we want to find out how fast do we need to spin this thing in order to get 110 volts out of it, right? Because remember, the faster you spin it, the more volts you get. So let's find out how fast we need to spin this thing. So we're going to plug in 500 for the number of turns. We're going to plug in the area in SI units, and then the magnetic field that's constant. And we're going to solve for omega. And when we do that, we get 15 radians per second. So the units of omega, okay, this is very important. We're kind of switching. We're not talking about degrees anymore, right? Radians per second is the unit for omega. It's not degrees per second, right? It's radians per second. So we could be, if we want to convert it to degrees, we could. Just for fun, right? We would, how many radians are in at 1 degree, or how many degrees are in 1 radian? 1 radian is, well, I'll tell you what, 1 radian isn't great. How about pi radians? We know that pi radians is 180 degrees, right? That's probably the best conversion factor to use. Or you could use 2 pi over 360. Or 360 over 2 pi. So that's how we would convert. Right, and that would get rid of the radians, and we have degrees per second, okay? If necessary. I'm not going to ask you to, I'm not going to ask you to do the conversion, but if you just wanted to picture in your mind, if you picture things better in degrees and you want to see how fast that is, that's really fast. Right? 15 times 180 over pi. Let's figure that out. That's 859 degrees per second. All right, so that's flipping that thing over like 2 or 3 times, right? Because it's 360 degrees per flip. So, I mean, you're flipping that thing almost 2 times a second, right? So it's really fast. It's almost 2 revolutions per second. Super fast to get 110 volts. Okay, so we're just, we're really plugging and chugging, but we need to fully understand what we're doing, right? Like, what are the units for frequency, the direction of the B field with respect to the rotation axis, right? We need to really carefully read these problems. And then once we get it, then the algebra is super basic. Let's look at this one. Okay, so let me erase this stuff real quick. We're going to do, this one's going to be like some unit conversion stuff that I was just talking about, all right? That's probably going to be the most difficult part here is the unit conversion into like rotational type units, like revolutions and radians and degrees, okay? So let's say that we decide to build a small generator, and we build it by rotating a coiled wire inside of a static. Static is another word for constant, right? Magnetic field of 0.3 Tesla. And then we construct the apparatus by coiling the wire into 3 loops of radius 0.16 meters. If the coil rotates at 3 revolutions per second, and it's connected to a device with 100 ohm resistance, what is the average power? So we're going to need average power. Let's scroll back up to, here we go, here's power, average power. All right. I guess I didn't go over that equation. I went over this one for power. Average power, you're going to notice that the sine squared goes away and you get a 2 under here, right? That's the difference between these two equations. The sine squared goes away and you get a 2, because what we've done for average power is we have averaged out the sine squared function, okay? And what that comes to be, it comes out to be half, right, of the max power. So that's exactly what we have right here. So average power will be omega squared, n squared, a squared, b squared over 2r. So we know that. So what is given in the problem? We got b, we got n, we got a, we got r. So what are we solving for? We're solving for omega. No, we're not. We got omega in a weird way. We're solving for p. Where's our omega? Well, we're told that the coil rotates at 3 revolutions per second. So 3 revolutions per second is kind of like another type of units that we want to figure out what is omega. If we're rotating at 3 revolutions per second. So how much is 1 revolution? 1 revolution, so if we go around a circle 1 time, 1 revolution is going to be 2 pi radians, right? Omega is in radians per second, so we need to convert to radians per second. So if we have 3 revolutions per second, 1 revolution is 2 pi radians. Boom, got rid of it. So we're going to have 3 times 2 pi over radians per second. 6 pi radians per second. That's our omega. Okay, so now we have omega. Boom, now we can solve pretty easily, right? So power average is going to be omega squared. Omega was 6 pi radians per second squared. 3 turns, 3 loops, right? The area is 0.16 radius, so pi times 0.16 meters squared. Oh, hold on. We got to make sure we get our squares right? We're going to square the radius, and then we're squaring that whole term. All right, so be very careful with your algebra here. That's the sneaky part. And then B was 0.3 Tesla. And then we're dividing all that by 2 because of the average. And then the resistance, 1 times 10 to the 2 is 100 ohms. All right, plug all that stuff in. Oh, we gotta square that. Times. Okay, kind of a pain to type on the computer, I will tell you that. Oh, my B is squared. Don't forget that. Okay. Divided by 200. All right, this is what I got. Let me check over my math. 6 pi squared, 3 squared, 3.14 times 0.16 squared times 0.3 squared over 200. All right, so I got 0.0093, and then the units of power is a watt, okay? Watts. So, 9 milliwatts, 9 milliwatts. Not a whole lot of power. Okay, we need to spin it faster, right? How can we get this to go up higher? We could spin it faster. We could increase the field. We could increase the area. We could decrease the resistance, right? To get more power, right? You're not going to be powering much with 9 milliwatts, right? If you look at like your iPhone charger, your iPad charger, the little brick. Let me grab mine. All right, I'm going to tell you how many watts this thing charges at. 12, right? 12, not 9 milliwatts, 12 watts. So we're going to need a lot more something to get more power, right? Spin it faster. More coils, more turns would definitely help. Larger area would help. Larger B field, smaller resistance, okay? Just give you an idea, conceptual-wise, what's going on here. So that wraps up this chapter, okay? I will post another video with some good review on right-hand rule stuff, finding the induced current. Okay, I feel like that's going to be the hardest part. This last part is pretty easy. Finding the induced current direction in situations like this, got the concept. Looking at this sliding bar, maybe the bar is moving the other way. Looking at many pictures like this where you got loops moving towards magnets, loops moving away from magnets, magnets moving away from loops. All right, every kind of variation. You need to look at all of those and be able to find the induced current direction, okay? And so I will post some examples of that for sure. You can find examples in the adaptive quiz for this chapter 20 adaptive quiz in modules. You can find more in the end of the chapter problems, okay? There's many places you could find example problems to do in order to help you get ready for this. I'll also post some sample exam style questions in a document along with the study guide, which I'll post a little bit later, okay? So let me know if you have any questions, all right? Have a good one.